In this video, we're going to talk a little bit about the details of the SN2 reaction specifically. So this is a specific type of nucleophilic substitution reaction. And we saw in the previous video how the nucleophilic substitution reactions substitute out that nucleophile for that leaving group. So that's what's going on about the alpha carbon. So in our case, we only had one carbon in our molecule, and that was the alpha carbon. But that's where that reaction is taking place. We're substituting out that nucleophile for the leaving group. What we saw with the mechanism is the fact that the nucleophile was actually attacking the alpha carbon and the leaving group was leaving at the same time. So we showed those arrows together. So what that's going to mean is that the rate of the reaction is going to be dependent on both the concentration of the nucleophile and the electrophile. We're going to need both of those. They're both participating in that reaction, in that rate determining step. And so we call this the second order reaction. And because both of those species are involved in the rate determining step, we also could call this a bimolecular reaction as well. So this SN2 reaction is a specific type of nucleophilic substitution in which both of the molecules are involved in that rate determining step. So the S in the SN2 stands for substitution, which is the what's happening structurally. Nucleophilic kind of gives an idea of how it's happening. So the nucleophile is coming in to actually kick off that leaving group. And the two is referring to the way that this substitution is happening and the way that there are two molecules that are involved in that rate determining step. So basically that means that this is all happening at once in one step or concerted. We're going to see another type of reaction, SN1, that goes through an intermediate and is stepwise, and so that's going to be a little bit later. So that's why we're going through what SN2 actually means. For another thing we're going to be considering is how the reaction goes in terms of drawing a reaction coordinate diagram. So this basically gives us, these reaction coordinate diagrams give us a way to visualize what's going on with the energy as the reaction is progressing. So we drew out the mechanism in the previous video where we had our nucleophile attacking the alpha carbon, leaving group is leaving, and we got our product with the alpha carbon now attached to what the nucleophile is. And so we substituted out that leaving group for the nucleophile. So we did that substitution and then our leaving groups by itself. Since we're making this bond from the nucleophile to the alpha carbon and we're breaking that carbon leaving group at the same time, we kind of had to do that. As this comes in, we can't overload that carbon with electrons. It can't have 5 bonds. And so that's why we kind of had to break that bond to leaving group right away. So because this is happening at the same time, we call this a concerted reaction. What the reaction coordinate diagram is going to look like, we have our energy on our y-axis, and on the x-axis we have our reaction coordinate or progress. So originally we started at a certain energy with our OH minus, our nucleophile, and our electrophile. As we're going to progress and as this mechanism starts happening, these two molecules have to start coming closer together. So what's going to happen with the energy as these two molecules come closer together is that it's going to rise. So we're going to have a certain peak, and this peak is going to be right when those bonds are forming and breaking. It's like a little snapshot of exact moment of when the nucleophile bond is starting to form and the leaving group bond is starting to leave. And then the energy is going to go back down after that key event, because then the molecules, which at this point are going to be the product and the leaving group, they're going to start to go farther apart from each other. Farther apart they go, less electron repulsion, energy comes down. And so these are going to be on the other side of our reaction coordinate diagram. So we can draw our products here. So at this very top, this is our transition state. We represent it as a kind of a little telephone pole looking symbol. This one is, that's a symbol for the transition state. We can also draw in that transition state. So in this case, we're going to center around that alpha carbon. So we're going to show that alpha carbon kind of on its side a little bit. So we're going to have the alpha carbon, and since we're looking at it on its side, we're going to make one of the H's come out of the page, the other one go back into the page, and then one of them be in the plane of the page. What's going to happen with the bond to the leaving group? We saw that one was breaking. So we're going to put a dashed bond, that's our partial bond to the leaving group, and then our bond to the nucleophile is forming at the same time, so we're getting that partial bond there as well. And another important aspect of this transition state that we're going to really be looking at to determine whether a nucleophile is good or whether it's relatively not a good nucleophile is the partial charges and what's going on with this transition state. So originally the oxygen of the OH is negative. As it starts to go in and do the attack, it starts to become neutral. So it's starting to lose its negative. That's going to be a delta minus on that. The carbon, the alpha carbon is always going to have a little bit of a positive charge because it's always going to be attached to something more electronegative than it. And so that's always going to be delta plus. Our leaving group is going to start to become negative in this reaction. It starts out neutral, ends up negative. So we're going to also have a delta minus partway through in that transition state. So this is what that transition state actually looks like. These bonds are forming and breaking at the same time. So we only have really that one jump in energy because we basically have that one mechanistic step. For stereochemistry, this is another important thing. We saw a little bit in our transition state. We kind of made that nucleophile and the leaving group on opposite sides of one another in our transition state. This is something that we know because when we look at that alpha carbon, if it's a chirality center, we actually see that we get an inversion of configuration. So that means that if we have the bromine coming out of the page, for example, in our electrophile, once we do the reaction, we have the nucleophile now going into the page. So we still did a substitution of the bromine for the OH, but we also had to pay attention to that stereochemistry. And so that OH actually comes from the exact opposite side of where that bromine carbon bromine bond is, the alpha carbon bromine bond. Why does this happen? This has to do with the orbitals. So we talked a little bit about orbitals earlier. The nucleophile is coming in with its lone pairs in its sp3 orbital. So this one is our nucleophile. It's negatively charged. And basically what's happening here is it's taking its orbital, its sp3 orbital in this case, with its lone pair, and it's going to overlap with the sigma star or the anti-bonding orbital for that carbon-bromine bond. And that anti-bonding orbital, that large part of that anti-bonding orbital is actually going to be exactly opposite to where the bond is at. So the bond is between the carbon and the bromine. The anti-bonding orbital, the major portions of the anti-bonding orbital are actually on either side of that bond. And so we're attacking the alpha carbon here. We're going to come in and start to overlap our nucleophile's orbital with our anti-bonding orbital because again, remember that when we're putting electrons into anti-bonding orbitals, we are actually breaking a bond. That's how we break bonds. And so that's why we're looking at the anti-bonding orbital specifically here. We're trying to break that bond. We're putting those electrons into that anti-bonding orbital. We see that that major part of the anti-bonding orbital is exactly opposite to where that bond is. So if this bond is coming out of the page, this anti-bonding orbital portion is going into the page, and that's where that OH is going to target. And so when it actually becomes the new sigma bond, because basically when these overlap, they're going to become that new sigma bond, it's going to be on the opposite side of where that carbon bromine bond or carbon leaving group more generally bond is. And then the electrons from that, the actual bond or from the carbon to the bromine are going to just end up as lone pairs on the bromine, which will be in its own sp3 orbital in this case because there are 4 things around the bromine, which means it's sp3 hybridized. So that's what's going on stereochemistry wise in this reaction. We always have to make sure that if we're starting with a chirality center, we're taking a look at where is that leaving group? How is it coming out of the page? What's going on with it? If it's coming out of the page, we're going to have our nucleophile going back into the page. If our leaving group is going back into the page, the nucleophile would be coming out of the page in the product because it does have to attack where that major portion of that antibonding orbital is, and that major portion of the antibonding orbital for that carbon leaving group bond is always going to be exactly opposite to where that bond is.